It's science time! This video goes over a worksheet about empirical formulas. Hopefully it will help your understanding of what they are and how they can be used. It was filmed last year, so please enjoy.
Alright, so we know what a molecular formula is. Molecular formula indicates how many moles of each atom is in 1 mole of that. How many moles of each atom is in 1 mole of that substance? So, for example, we've got lovely H2O. For 1 mole of water, there are 2 moles of hydrogen and 1 mole of oxygen. Now, when we are doing the empirical formula, we are giving it as a ratio because we can't say the exact amount of moles per mole of sample, but we can say, like in the shared example, that for every 1 oxygen, there are 6 hydrogens and 2 carbons. Or for every 2 carbons, there are 6 hydrogens and 1 oxygen. This might not be its molecular formula. It might be, but chances are it's not. There's a lot of carbohydrates that actually fit that criteria. So it's almost like how we had that general formula that you can have for alkanes, how they're like CN and then H is N plus 2. Oh, sorry, 2N plus 2. It's kind of like that, but it's not, basically. It's just, it's a ratio. So let's go through this worked example. I really liked this Purple Monkeys drink rum. I tend to like not to like mnemonics. But it's kind of interesting, so it's fine. So we've got our example, which is calculate the empirical formula of a compound that has a percentage composition of 52.2% carbon, 13% hydrogen, and 34% or 35% oxygen, pretty much 34.8. So how the percent composition looks is a little bit like this. So that didn't work how I wanted to. So the blue is the percentage of carbon, the hydrogen is green because we only had 13%, and the pink is how much oxygen we had. Now, because you guys know that your percentage that you have is not the same as the number of moles. Why? Because your number of moles is the number of particles you have. The number of particles is you don't calculate that from percentage composition. This just is like, this is how much there is. And how they find the percentage composition for things is they will actually burn it. They'll burn the unknown sample and then they run it through a machine that gives you a spectra, and then it will tell you how much of your sample is which atom. It can tell you the type of atom. It cannot tell you the moles of the atom, which is why we go to our next step. So before we go on to that next step, I wanted to show you this close up. So this is our percent composition. You can see that if we just look at the percentage composition, there looks like there is, I'm just going to hold this. It looks like there is hardly any hydrogen and a lot of carbon and sort of maybe like 3/4 of your oxygen to your carbon. We already know from looking at the answers that that is not what our empirical formula looks like. Our next step, we calculate the moles of the atom, of each atom, by first, we assume that the sample we have is 100 grams. Why? Because quick maths. So because it's 100, we can change our percentages into grams. So instead of being 52.2% of carbon, we have 52.2 grams per 100 grams of carbon. Okay, so we've figured out what our percentograms is, and now we're working out our moles. Now I wanted to give you guys a little visual. So this is our moles, say if it was like a bar graph. So again, hydrogen is green, oxygen is pink, and carbon is blue. Oh, hopefully this isn't going to fall out. By looking at this, so this is the actual amount of, this is the actual number of particles that are in the sample. Now when you see it like this, it is very easy to see that you've got about double the amount of carbon that you do of oxygen, and with hydrogen, and like obviously it's me, these aren't to scale, with hydrogen you can tell that there's about 6 times as much hydrogen as there is oxygen. Now how to get this into the smallest ratio, right? Because we do have a ratio that we've worked out, which is the whole divide. Yeah, because this is literally saying that for every 100 grams, there are 4 moles of carbon. But to get the smallest amount, which is what we want it to be nice and small. Think of it as if you're going from 2/4, we want that to be 1/2. So we're simplifying our formula. So to simplify it, you divide it by the smallest amount of moles. Why? Because you can't have less than that. You have to have at least 2.175 moles in your 100 grams or it just doesn't work. You will find that with our examples, there will be things like this. We get 5.97. I thought this little EG bit was kind of confusing, but I sort of left it there in case you guys understood it. But I think what it's basically saying is if you don't get nice, like clean numbers that are easily rounded, because it's only like 0.01 that you need to change or something like that, then you need to multiply it to get a nice whole number, which we might find as we go through our examples. So now we are going to go through the worksheet. Let's do the worksheet. I have my handy dandy phone next to me to be a calculator and also to look up our periodic table as needed. So let's start with this question. Okay, glucose is a sugar. Cool, knew that. Which has a mass composition of 40% carbon, 6.7% hydrogen, and 53.3% oxygen. So first let's do our masses. So our mass of carbon is equal to, in a 100 gram sample, 40 grams. The mass of hydrogen, however, is 6.70 grams. And last but not least, our mass of oxygen is 53.3 grams. What did you notice about all of those values? They're in 3 significant figures. So just a little ad lib about significant figures. See how this says 40.0% carbon? That means that 0, the actual amount, it could be 39.999%, Or it could be 40.01%. We don't know. We only care about the 3 significant figures because we can say that our machine is accurate to 3 significant figures. Boom. All right. Now we want to work out our moles of our substances. So let's figure out how many moles of carbon are in this 100 gram sample. So we go 40g over, actually I'm just going to quickly Google it. See molar mass, I'm pretty sure it's 12. Boom, it's 12. Lovely. Over 12 gmol. Where to go? And you don't press enter, you go 40 divided by 12, it comes up with our answer. Grams per mole of, oh no, just mole. Why? Because our grams cancelled out and our mole moved up to the top. Now we can work out our moles of hydrogen. Hydrogen's nice and easy because it's divided by 1, so you just go, to prove to the marker that you know your stuff, you go 1.00 gmol equals, oh my god, hard as to figure out this one, 6.7 moles. Then to work out our moles of oxygen, we go 53.3 G divided by 16 grams per mole. And that will give you an answer. 53.3 divided by 16, 3.33125, which actually rounds up to 3.33. So this is already telling you that you've got the same amount of carbons as you do as oxygens. Wild. Then we need to divide everything by our smallest amount. So we go ratios. So for C equals 3.33 divided by 3.33, 1 carbon. For our hydrogens, it is 6.7 divided by 3.33, which is roughly half. What does that give us an actual answer? 3.53, that gives us 2.01, so I'm just going to round that to 2. And for our oxygen, again we have 3.33 divided by 3.33, which equals 1. So the answer is CH2. I still can't figure out how to make my subscripts on Google Docs, so if you could teach me how to do that, that'd be cool. And 1 oxygen there, and yeah, that could be a super long sugar chain, it could be a really short sugar chain. If you had a polymer of glucose, which you do get, the polymer would actually still have the same empirical formula, which is a bit interesting. So let's go through into this next example. This time we're using caffeine, so we need to work out the following masses. So I'm just going to go straight into our masses for this one. So I'm going to go straight 49.5 m, and then hydrogen is 5.2. Then our nitrogen is 28.9. And our oxygen is 16.5. Cool. So let's do this again. So our moles for carbon first is, it actually doesn't matter which order you do the atoms in, by the way. I'm just following the order of the question because for me that is easier, because that means it's easy for me to check to see if I've missed a step. So mass over molar mass, 49.5 grams divided by 12 grams per, that's annoying, grams per mole equals 4.12 mole. The moles of hydrogen equals 5.2 mole. Our mole of nitrogen is 28. I can't remember the molar mass of nitrogen, or the atomic mass. I think it's 14. So let's try this. 28.9 grams divided by the G mole. I was very wrong. Oh, wait, its atomic number is 7, which means its atomic mass is 14. Yes, I'm right. Look at me go. Which is equal to 2.06. And last but not least, we need to work out the moles of our oxygen. 16.5 G divided by 16 grams per mole equals 1 mole. So this is a nice easy one because we're literally just dividing everything by 1. What happens when you divide something by 1? It just stays the same. So we can already type up our thing. So there are, remember these are subscripts. I just cannot figure out how to make them small. So we have 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. Now, if we wanted to figure out what its actual formula is, all we need to do first is find out the molar mass of the molecule. So if you have the molar mass of caffeine, which hopefully when I search this up, it's not going to come up. Actually, I don't want to spoil the answer, the surprise. I'm going to search up the molar mass of caffeine on my phone. So it is 194.2 grams per mole. All you do is you add together the molar mass of what you've got here. So you go 4 times 12 plus 5 times 1, which is still 5, plus 28, plus 1, not 1, 16, sorry. Okay, so that will give us a number doing this on my calculator this time because there are a few numbers. Plus 5 plus 28 plus 16 equals 97. So we're going to say 97 grams per mole. Actually, I'm not going to give it a number because this is just, well, I will. It's the molar mass of our empirical formula. So I'm just going to write that in brackets. Cool. Then we get that number and we go 97 divided by 194.2 gives you 0.49999, which means you need to double the number of, let me do this a better way. So if you go, this will be an easier way to understand, I promise. If if you go molar, if you go actual molar mass of the molecule over molar mass of empirical formula, that'll give you a number. In this instance, it will give you 2. You times this coefficient, so multiply this coefficient by the empirical formula. So that means the real molecular formula for caffeine is C8H10N4 and O2. So that's me.
Thanks for watching this episode of Science Time with Kate. I hope this really helped your understanding of empirical formulas and how you can sort of manipulate them and use them in analytical chemistry. If you have any questions, please comment below, or if you know my email, email me. Have a beautiful day. Ka kite anō.